Hello everyone, I hope you're all doing well. We will be solving a problem on components versus projections. And here is the problem. Okay, so problem. So I have two directions that are already given to me in this problem. So one of them is the vertical direction, which I'm going to label as little v. And then there is another direction that is drawn at an angle to the vertical direction, which I'm going to call as the direction little u. Then I have a force that is drawn from the point of intersection of these. Okay, so here is the force. This is the force F. I'm given the magnitude of the force F. Okay, so I'm given the magnitude of the force F as 150 newtons, and I'm also given a couple of angles. One of them is this angle right here, which I'm marking, which is given as 105 degrees, and another is the angle made by the force F with the u direction. So these are all given to me. Okay, the angles 105 degrees and 30 degrees. These are the things given to me. What do I need to obtain? Obtain the components of the force F along the u and the v directions. Components of F along the u and the v direction. Okay, and then I also need to obtain the projection of F along u and v. Okay, and this is something, if you have seen the lecture notes, you will realize that since the directions u and v are not orthogonal to each other, the components and the projections will not be the same. Okay, before I start going into the components and the projection, I can do a little bit of trigonometry or geometry here, and then I can find out the following. You see, I know this angle of 105 degrees, which means that this angle here is going to be 180 minus 105, which is 75 degrees. And likewise, if I know the angle here to be 30 degrees, and if I know this angle to be 75 degrees, then this angle here is going to be 180 minus 30 minus 75, and if you do the math, this is going to end up as a 75 degree angle as well. Okay, all right. So with this having in mind, we will now take the same figure, and then I'm going to copy this figure, and I'm going to start looking at the components first of all, and then we will look at the projection of the force along the directions. Okay, so let's start with the components. So components of F. Okay, all right. So I'm going to paste the figure from before, and there are certain things that I'm going to get rid of. First of all, I will say that, okay, we already know this to be 75 degrees, so I'm just going to write it out as 75 degrees. Okay, and I had it in the same color before, so this is 75 degrees that is known to me. Okay, and we know that this is given to us, so I can get rid of that. All right. Now, in order to find the component of the force F, what do I have to do? From the head of F, I have to draw a line that is parallel to the u direction and parallel to the v direction. And this is precisely what I'm going to be doing. Okay, so from the head of F, I'm going to draw a line parallel to the u direction. And here is what I'm doing. I'm doing that right here. Okay, then likewise, from the head of F, I'm going to be drawing a line parallel to the v direction, which is what I've done here. Okay, these are parallel lines, so I'm just going to draw them as dotted lines. Okay, and of course we don't need the extent of the lines that I've drawn here, but it doesn't hurt us at all. Okay, and then once I know that, okay, these are the points of intersection, as you can see, there is a point of intersection right here, and then there is another point of intersection right here on the u and the v directions, then I know that starting from the tail of the force F all the way to where the points of intersection are will give me the components. Okay, so starting from the tail all the way on to here is going to be the component of F along the v direction, along the u direction, I'm sorry. So this is going to be F u component. And then likewise, if I start from here and then go all the way there, and pointing in this particular direction is going to be F in the V direction. This is the component. And of course, since we have a parallelogram, the opposite sides must have the same length, which means that if I am writing the magnitude here, that is also going to be the same value as F suffix U comma C, right? And if you want, you can also write this magnitude as the same as before. Okay, you can write this as F V suffix C. All right. Now, what I have to do is I have to make use of some trigonometry, and before I do some trigonometry, I need to focus on any one of the triangles that I'm interested in. So I'm going to shade the triangle I'm interested in. So okay, so here is the triangle that I am interested in, and in this triangle you can obviously see that one of the angles is 75 degrees. If I look at this 30-degree angle here, I know that the line U and the line parallel to that are parallel lines, which means that I have alternate angles equal to each other, so which means this is also 30 degrees. If I have two angles of a triangle, the third angle is found by subtracting 180 degrees from that, which means that if I look at this angle here, this is going to be 180 minus 30 minus 75, so that's going to be 75 degrees as well. Okay, and so I'm going to take a look at the shaded triangle. Okay, so take a look at the shaded triangle. And in the shaded triangle, I know the magnitude of the force F, and I know three angles of this triangle, which means that by making use of the sine rule or the cosine rule, I can find the remaining sides, and that's precisely what I'm going to be doing. Okay, so if I take the shaded triangle, and I'm going to just redraw that maybe in the next page. Okay, so I'm going to take this line and then bring it down here. Okay, and here is the shaded triangle. I'm going to get rid of all the different colors. Okay, so here is one side of the triangle, and then here is another side of the triangle, and then the third side of the triangle. Okay, this was supposed to be the force F, which was having a magnitude of 150 newtons. Okay, then I have this as Fu comma C, and then this is F V comma C. This angle was known to me, this angle was known to me, this angle is also known to me. This was 75 degrees, this was 30 degrees, and so this remaining angle is also 75 degrees, and this is the same shaded triangle that we have from above. Okay, and then if I know one side of the triangle, I know all the three angles, I can use the law of sines or the sine rule. Okay, so that's exactly what I'm going to be doing. Okay, so use the law of sines or the sine rule. I like to call it as a sine rule. Okay, so if I use the law of sines, then the length of a side divided by the sine of the angle opposite to that side should be equal to the other respective lengths divided by their sine of the angles. So if I take the force F, right, so then F divided by sine of the angle. So you look at the force F, the angle opposite to that is 75 degrees right here, right? So this is going to be sine of 75. That's going to be equal to F VC divided by the sine of the angle opposite to that, which is sine of 30 degrees, and this is going to be equal to FUC divided by the sine of the angle opposite to that side is sine of 75 once again. Okay, or you could have been a little smarter. I'm not that smart, so I did not realize that this was an isosceles triangle, and you can immediately see that, okay, if two sides of the triangle are having the same angles, if the angles are the same, then the two sides length should also be the same. So F U suffix C is eventually going to end up being 150 newtons. But let us let the sine rule take care of that. You know, we don't need to think too hard. Okay, so from this I can say the following: F U comma C by sine 75 is equal to 150 by sine 75, because the force F is equal to 150. This is because, this is my sign for because F is equal to 150 newtons. which means that if I do the cross multiplication, F u comma c is going to be 150 newtons as well. Okay, so this is the component of F along the u direction, and likewise I can do the component along the v direction. That's going to be F vc. I can take that divided by sine of 30 degrees. I can either take the ratio FUC by sine 75 or F by sine 75, because I found out FUC right now, right? So this is going to be, let me just consider F by sine 75, which means that F v comma c is 150 times sine of 30 cross multiplied and divided by sine of 75, and which eventually tells me that F v comma c, if I do the math, that's going to give me approximately 77.6 newtons. All right, so these are the components which we have found out. Okay, so this is the component along the u direction, and this is the magnitude of the component along v. Okay, now how to find the projection? If you have gone through the lectures, you will realize that the projection is obtained, a projection of a force along a direction is obtained by just dropping a perpendicular from the head of that force onto the particular direction. Okay, so that's precisely what we're going to be doing right now. Okay, so I'm going to be going on to a new page. Okay, so let me look at the projections. Projection of F, okay, along u and v. All right, and I'm hoping that I have my figure from before. That might, I guess not. Okay, all right, so if I do the projections, I'm going to redraw the directions very quickly. Okay, all right, I got that done. Then I got this guy done here. So this is the v direction, this is the u direction. I have the force F that is given to me here. Okay, this is the force F whose magnitude is known to me. All right, now how to find the projection along the u direction. So this was supposed to be the u direction, something happened there. That's the problem with technology, is that you never know what's going to happen. At any point in time, perhaps my iPad is going to break down, but who knows? It hasn't happened so far. All right, I'm thankful for that. So I'm going to drop a perpendicular from the head of F onto the u direction. Okay, so starting from here, I'm going to drop a perpendicular down here. Okay, so this angle is going to be 90 degrees, which means that this length here is going to be FU projection. Likewise, if I have to find the projection along the v direction from the head of F, I drop a perpendicular onto the v direction, and you will see that, okay, distance from here all the way to there is going to be FV projection. Now we know the angles inside from before, so I'm not going to go over that again, but this angle was 30 degrees, and that angle there was 75 degrees. Since both of these are right angle triangles, and of course this was the force F that was acting right there, the magnitude of the force F is known to me. I need to find force F V and then force F U suffix P, and that's fairly straightforward. Once I know the angle, they are just the cosine of the angle times the magnitude of the actual force. Okay, so this tells me that F U suffix P, the magnitude of the projection, is F times cosine of 30 degrees, which is 150 times cosine of 30 degrees, and that's going to be approximately 129.9 newtons. And then likewise, F VP is going to be F times cosine of 75 degrees, which is going to be 150 times cosine of 75. And sometimes I write the degrees, sometimes I don't. I'm not very particular about it. It's okay with me if you just write it as 75 without the small o on top as a superscript. This is approximately 38.8 newtons. Okay, so these are the projections of F along U and V. And it is very clear. So if I bring out the components, right, let me do that. Let me bring the two components down here. Okay, so these are the one of them, which is right here. Okay, here is one component, and here is the other component. Okay, I just want to make a very brief statement, which you already know and which you probably already realize. So these are the projections. I guess I'm going to have a different color for them. Okay, and this is the projection as well. Okay, and you can immediately see that because the directions U and V are not orthogonal to each other, the magnitude of the projections is not the same as the magnitude of the components. Okay, so because U and V are not at right angles to each other, the component of F are not the same as the projections of F along the U and the V directions. Okay, so that is a key idea here in this problem that is reinforced again. This is because U and V are not at right angles to each other. But if they were, as you would see in a Cartesian coordinate frame, then the component would be the same as the projections, but that is unfortunately not the case here. And the next problem that we will be solving, which I'll post as another video, is looking at components along the Cartesian coordinate frame. All right, thank you very much, and stay safe.